Alright, so this is 6.8, our last part of Chapter 6, and it's all about exponential growth and decay. Now, most exponential growth and decay follows this model. A of t equals a sub 0 e raised to the kt, or a equals a sub 0 e raised to the kt. In these models, a is your amount after a time, a sub 0 is your initial amount, e is our natural base number, k refers to the rate at which it's growing, and then t is a time. Now, if k is a positive number, if k is bigger than 0, then this function models a growing entity, and it is an uninhibited growth. It keeps growing and growing and growing. If k is a negative number, less than 0, then this is a decaying entity, and it's going to keep going smaller and smaller. It's called uninhibited decay. So depending on what value you get for k, you can end up with growth or decay. It just kind of depends. So let's look at an example. Example 1 says, in 1970, the U.S. population was 203.3 million. By 2010, it had grown to 308.7 million. Part A asks us to find an exponential growth function that models the data for 1970 to 2010, and to treat 1970 as t equals 0. Identify the initial population and the growth rate. Well, we can already identify the initial population because 1970 is times 0, and they told us in 1970 it was 203.3 million. So a sub 0 we already know is 203.3. For the rate, though, we're going to actually have to solve an equation. So we're going to have to kind of fill this in. So right now we don't know a. We know a sub o is 203.3. We have e. We don't know k, and we don't know t. But we can actually solve for k because they gave us a second data point. They told us in 2010 the amount was 308.7. So I can plug in for my a, my amount, 308.7 equals 203.3 e to the k. And I can plug in t because t is time since 1970. So how many years is it from 1970 to 2010? Well, it takes 30 to go to 2000, and then 10 more to get to 2010, so that's 40 up here. So k times 40. So what we're going to do is we're going to divide both sides by 203.3. So we'll have 308.7. Sorry, I'm going to go back and rewrite that 3. 308.7 divided by 203.3 equals e to the 40k power. And to get rid of an e, we can do an ln. So ln of 308.7 over 203.3 equals ln of e to the 40k. The ln and the e can cancel out. So ln of 308.7 divided by 203.3 equals 40k. And then I'm going to divide both sides by 40 to get my k value. So k equals, my calculator, I have a natural log of 308.7 divided by 203.3, and then I'm taking that natural log and dividing it by 40, so there's my k, 0.010. So that's my growth rate. And so that means my equation is going to be a equals 203.3 e to the 0.010 t. Now here's the thing. I am going to keep all these decimals. I'm going to show you a different technique to do that. I'm actually going to tell my calculator to take this answer and store it. And we're going to store it in the letter k. Now you might notice the letter k here is in green, so I have to hit the alpha button first, and then hit k, and then I can hit enter. And so now, if I ever just type in k, and I hit enter, it'll tell me that that's what the k value is. And so I can kind of keep it stored. I don't have to remember it. I don't have to write down all those decimals. I can just kind of keep it stored in there. Alright, so that was part A. Part B asked what was the population in 1985. Well, how many years is it from 1970 to 1985? Well, that's 15 years, so we want t to equal 15. So we'll have a equals 203.3 e to the 0.010 times 15. So 203.3, I got an e, and then I'm going to put my k in there, and I'm going to multiply that k times 15. There we go, 237.773. And that is measured in millions. So that's how many million people were in the U.S. in 1985. Right. Part C asks, by which year will the population reach 335 million? So this time they've given us an amount, so we're going to plug in for A. 335 equals 203.3 e to the 0.010 t. Divide the 203.3 across, so 335 over 203.3 equals e to the 0.010 t. Take a natural log, so natural log of 335 over 203.3 equals, on the right-hand side, we know the natural log and e will cancel, so this is just going to be 0.010 t, and then we just divide across that 0.010. Okay. And so we get t equals, and then we'll go to our calculator. So I'm going to do a natural log 335 divided by 203.3. And then that natural log gets divided by our k value. So I'm going to say, hey, let's divide that by the k. And there we go, 47.829. Oh, no, that'll round up 830. So 830 years, which really means that it's 1970 plus 47 years. So it's in 2017. So apparently, according to this model, this year is the year where we will get up to 335 million. All right. Part D asks, what is the doubling time for the population? So we have to double this. So let's take 203.3, multiply it by 2. There's our new amount, 406.6. So 406.6 equals 203.3 e to the 0.010 t. When we divide that over, we're just going to get 2. So 2 equals e to the 0.010 t. Take a natural log. Natural log of 2 equals, over on the right side, the natural log and e will cancel, so we'll just have 0.010 t. And then divide that across. So we have natural log of 2. And then we're going to divide that by our k value. And so we get 66.380. 66.380. And that will be measured in years. Okay. And that time we can leave that as years because it asks us what is the doubling time. This is the amount of time it took to double. Okay. And so that's how the problem works. That's how a lot of these problems are going to work. You're going to get some information, you're going to use it to find either your initial population or your k or both, and then you'll write your equation, and then you'll use your equation to solve some problems. Let's look at number 2. Number 2 says a colony of bacteria increases according to the law of uninhibited growth. Part A says, if the number of bacteria doubles in 3 hours, find the function that gives the number of cells in the culture. Okay, well, remember our formula looks like this. Okay. So for part A here, Do we know the initial amount? No, they didn't tell us, so we're going to leave that as a sub 0. E is just our math number, so we'll leave that in there. Do we know the k? No, we don't know the k yet. Do we know the t? Well, they told us it doubles in 3 hours, so we know t is 3 equals. Do we know our final amount? Well, it told us it doubles, so it takes whatever this initial amount is and it multiplies it by 2. So we'll have 2 times the initial amount, 2 times a sub 0. And then we'll divide the a sub 0 across, and so we'll get 2 equals e to the 3k. Take a natural log on both sides, so natural log of 2 equals 3k. Divide both sides by 3, and we can figure out what k is. Natural log of 2 divided by 3, so it's 0.231. And again, I'm going to store that value, so I'm going to say, hey, let's store that in k. So now when I hit k, it'll give me that number. All right, so now we have a model. We can say a equals the initial amount times e to the 0.231t. And that's really all we can do because we still don't know the initial amount, so we still can't fill that in. So this is the best model we can have, the best equation we can have. All right, part B asks us how long will it take for the size of the colony to triple? Well, if it triples, that means it's 3 times the initial amount. So we'll have 3a sub 0 equals a sub 0 e to the 0.231t. Divide the initial amount across, so you'll get 3 equals e to the 0.231t. Take a natural log on both sides. Natural log of 3 equals 0.231t. Divide the 0.231 across. So in my calculator, I'm doing natural log of 3, and then I'm dividing that k value across. And so we get 4.755. And that would be measured in hours in this problem. Time is measured in hours here. So 4.755 hours is the amount of time it takes to triple. All right. Part C asks how long will it take for the population to double a second time, which another way of saying that is the original population increases by a factor of 4. The original population quadruples. So that means we're going to have 4 times the initial amount equals the initial amount e to the 0.231t. Divide the initial amount across. 4 equals e to the 0.231t. Take a natural log on both sides. So natural log of 4 equals 0.231t. Divide the 0.231 across. Natural log of 4 divided by our k value ends up being 6. It comes out as exactly 6, which is nice. Okay. So again, that's kind of how these problems work. All right. Example 3 says atoms have a characteristic called a half-life, meaning that after a certain period of time, half of that atom will remain, half of the amount. So it basically decays by half after a certain period of time. Part A says use the fact that after 5,715 years, a given amount of carbon-14 will have decayed to half the original amount to find the exponential decay model for carbon-14. So again, remember this is our formula, A equals A sub 0 e to the kt. Do we know the initial amount? No. E. Do we know the k? No. Do we know the t? Yeah, we know the t is 5,715. Equals. Do we know the final amount? Well, they told us after this much time, it has decayed to half of the original. So 1/2 times the original. Divide the original amount over, you get 1/2 equals e to the 5,715k. Take a natural log on both sides, so natural log of 1/2 equals 5,715k. Divide the 5,715 across to get your k value. So natural log of 1/2 divided by 5,715. You might see that it has this notation, negative 1.212855596 e to the negative 4. That means it's times 10 to the negative 4. So that means this decimal needs to move 4 places over to the left. So it's a negative 0.0001, basically. Because if you move that decimal, it was right here next to the 1, you move it over 4 places to the left, and that's where it ends up. And there's these zeros to fill in here. So there's our k. So our amount equation would be this. Now again, I am going to store that value for k because I don't want to have to remember it. So I'm just going to say, let's store that into k, and just double check. Yep, we got our k in there. Okay. So there is our model. All right, part B says, in 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found by an Arab Bedouin herdsman. An analysis indicates that the scroll wrappings contain 76% of their original carbon-14. And so they asked us to estimate the age of the Dead Sea Scrolls. Okay. So they have 0.76, 76% of the original amount. So of the original equals the original amount, e to the negative 0.001t. Divide the original amount across. So you get 0.76 equals e to the negative 0.001t. Take a natural log on both sides. So natural log of 0.76 equals negative 0.001t. And then divide the negative 0.001 across. So natural log of 0.76, divide that by our k. And there we go, 2262.732. And that would be measured in years, because that's what the time was measured in. So when they found them, this is how old they were. So this is how old they were in 1947. Well, if we wanted to figure out how old they are today, we can just figure out how many years it's been since 1947. So 2017 minus 1947, it's been 70 years. So we just need to add 70 years to that. So 2262.732385, add 70 years. So it's been 2,332.732 years, and that's for now in 2017. So that's kind of how it works. Not too bad. All right, let's keep on going. We have another little formula here. This is called Newton's law of cooling. This is about how objects cool when let's say you take a hot object and you just put it down on a table. Well, the temperature in the room is different than the temperature of the hot object, and so over time, you'll kind of reach an equilibrium, and the temperature of the hot object will lower until it becomes close to the temperature of the surrounding medium. Okay. So the formula we use for Newton's law of cooling looks like this. U of t equals t plus u sub 0 minus t times e to the kt, where k has to be less than 0. In this thing, T here represents the temperature of the surrounding medium, the temperature of the room the object is in. U sub 0 represents the initial temperature of the heated object. And then K is just going to be our rate. It's going to be a negative rate. And we'll have to figure it out. So let's look at an example of Newton's law of cooling. An example 4, it says an object is heated to 100 degrees Celsius and is then allowed to cool in a room whose air temperature is 30 degrees Celsius. So this 100 degrees Celsius is our U sub 0. That's the initial temperature of the object. This 30 degrees right here, this right here is the T. It's the temperature of the room. So if we kind of fill in what we know right now what we have is U of T equals 30 plus 100 minus 30 times e to the kt. That's what we have right now. And we can actually clean that up a little bit. So this is 30 plus 100 minus 30 is 70. E to the kt. So that's what we're at right now. Now, part A says, if the temperature of the object is 80 degrees Celsius after 5 minutes, when will its temperature be 50 degrees Celsius? So they kind of give us a data point. It says that it's 80 degrees after 5 minutes. So I'm going to plug 80 in here for the temperature, and I'm going to plug in 5 for the time. And then I'm going to solve this equation. We're going to solve for k, figure out what that constant is. So subtract the 30 across. 80 minus 30 is 50 equals 70 e to the 5k. Divide the 70 across. So 50 divided by 70 is the same thing as 5 over 7 equals e to the 5k. Take a natural log. So a natural log of 5/7 equals 5k. And then divide by 5 to get your k. So natural log of 5/7 divided that by 5. There's my k. Negative 0.067. And again, I am going to store that into the letter k, so that way I have it in there, and I can verify that it's actually in there. Alright, so now we have that. So next, it asks us, when is the temperature going to be 50? So we're going to fill in 50 for our temperature now. 50 equals 30 plus 70 e, and now we know the k is negative 0.067. But we don't know the t because they're asking us when. They're asking us to find time. So subtract 30 across. 50 minus 30 is 20. Equals 70 e to the negative 0.067t. Divide the 70 across. 20 divided by 70 is the same thing as 2 over 7. Equals e to the negative 0.067t. Taking a natural log on both sides. And divide the negative 0.067 across. So natural log of 2 divided by 7, and then divide that natural log by our k number. There we go, 18.616. And that is measured in minutes in this problem. It takes 18.616 minutes for the object to reach 50 degrees. Alright. Part B asks us to determine the time when it gets to 35 degrees. So it's the same kind of thing here. We're going to plug 35 in for our temperature. So 35 equals 30 plus 70 e to the negative 0.067t. Subtract the 30 across. 35 minus 30 is 5 equals 70 e to the negative 0.067t. Divide the 70 across, and just so you can see, 5 divided by 70 is this decimal, but I can change it to a fraction really quick. It's 1 over 14. So 1 over 14 equals e to the negative 0.067t. Take a natural log. Natural log of 1 over 14 equals negative 0.067t. Then divide that negative 0.067t across. So the natural log of 1 over 14, divide that by our k number, and we get 39.217. Again, that's measured in minutes. So that's how long it takes to get it down to 35 degrees. Alright. Part C asks us, what do you notice about the temperature as time passes? So as time goes to infinity, what's happening to the temperature? Well, if you think about it, over time, if you have an object and it's just sitting in a room, it's going to get gradually cooler and cooler until it's the same temperature of the room. So in this case, it's going to keep going until it gets to 30 degrees Celsius. Okay. It's never going to quite get to 30 degrees Celsius. It'll get really, really close, so close that we really can't tell the difference. But you know, it'll approach 30. It'll get closer and closer to 30. Okay, so that's what wall cooling. It's not too bad. Alright, the last thing we're going to look at is logistic growth. So logistic growth is when your function has a certain maximum that it's going to reach. It has an upper limit that it cannot exceed. So most exponential functions, they look like this. They just keep growing and growing and growing. Logistic ones kind of look like this. They grow, and then they reach a maximum, and they flatten out. Okay. So it kind of grows for a little while, just like this one does, but then it flattens. So the model that we have for logistic growth is this. A equals C over 1 plus AE to the negative BT power. In this, the big A here is your amount after a time. C on top is the carrying capacity. It is the highest amount. It is what you flatline at up here. Okay, this A down here is just a constant of some kind. The B here next to the T is a rate of some kind. It's a rate at which things are changing. And then T is time, of course. Okay. So let's look at a logistic growth problem. So example 5 here says the function f of t equals 30,000 over 1 plus 20 e to the negative 1.5 t describes the number of people f of t who have become ill with the flu 2 weeks after its initial outbreak in a town with 30,000 inhabitants. Part A asks how many people became ill with the flu when the epidemic began. Well, when the epidemic began, that means we need to go to t equals 0. So we're just going to plug 0 in for our t. So f of 0 equals 30,000 over 1 plus 20 e to the negative 1.5 times 0. And then go to your calculator. 30,000 divided by parentheses 1 plus 20 e raised to the negative 1.5 times 0. That closes the e, and that one closes the bottom of the fraction. So here we go, 1428.571. Now here's the thing. Because we are talking about people, you can't have 0.571 of a person. We do need to round it to a whole number. So this is 1,429 people. Part B asks how many people were ill by the... So now we're looking at t equals 4. So f of 4 equals 30,000 over 1 plus 20 times 4. And then go to our calculator again. So divided by parentheses 1 plus 20 e to the negative 1.5, this time times 4. Close the e, close the bottom of the fraction. And there we go, 28,582.997. And again, because this is talking about people, you have to round it, so it's 28,583 people. Part C asks, how long does it take for 2,500 people to become ill? So this time they gave us an amount, so we're going to plug it in here for the f of t. So 2,500 equals over 1 plus 20. And what we're going to do is we're going to multiply both sides by that 1 plus to the negative 1.5t. So I'm actually going to do that on both sides. Over here on the right side, these will just cancel out. And so I'll just have, I'll just have 30,000. Over here on the left side, I have to actually distribute the 2,500 into the parentheses. So 2,500 times 1 is 2,500, plus 2,500 times 20 is 50,000. And then that has an e to the negative 1.5t attached. Then we take this and we subtract it, so we have 50,000 e to the negative 1.5t equals, let's see, 30,000 minus 2,500 is 27,500. Then we would divide the 50,000 across. So I'm going to take that 27,500 and I'm going to divide it by 1,000. So that's 0.55. Then we'll take a natural log on both sides. So negative 1.5t equals natural log of 0.55. And then you would divide the negative 1.5 across. So natural log of 0.55 divided by negative 1.5 gives us, I think I typed something wrong. No, maybe not. That'd be 0.399 weeks, which a week has 7 days, so that means it only really takes 2.790 days. So it actually doesn't take for it to hit 2,500. And I guess that kind of makes sense because at the very beginning we already had 1429. So it kind of makes sense that it got to 2,500 pretty quick. Alright, last part, part D. Part D asks, what is the limiting size of f of t? What is the carrying capacity, basically? Well, again, look at the number here at the top. It's 30,000. And that makes sense in the context of this problem. This town only has 30,000 people in it. So the most number of people who can get infected is 30,000. I can't get up to 30,001 because there's not 30,001 people in this town. There's only 30,000. So the highest the number of people infected get is 30,000. So that's as much as it can ever get. Okay, that wraps it up here for 6.8. And as always, if you have any questions, please feel free to